Thank you everyone for attending part 2 of exploring the power flow dynamics. And I'll be taking into more of like a fluid mechanics and PSV stability route. We went over this a bit in yesterday's part 1, but essentially the new 1D dynamics in 11.6 has all these control of the boundary conditions of the 1D dynamics model. And these boundary conditions are essentially allow us to better define and be more creative in defining geometries and also solving problems as well. And one key feature is, again, these scale terms in red. And I mentioned briefly that I would go over this in my part 2, and I'll basically use this as a good example. These scale terms in red can allow multiple boundaries, and this is actually what allows us to add multiple relief devices on the same line. So later you'll see an example of multiple devices, relief devices on the same inlet line. So basically what we'll be able to see is how the pressure waves all interact when all these PSVs open at different pressures and set pressures, different positions, all on the same line. So it's a very advanced technique, and it's very, very good, especially when you do an engineering analysis to evaluate stability. It always talks about stability in a sense of almost like simple geometry, simple piping. Well, with this these caveats to the PDEs, the partial differential equations, we can actually add more boundary conditions to our engineering analysis. So that's the key, I think, addition to the 1D dynamics that we have in SuperChems. So what do I mean by multiple PSVs and PRV objects? Well, essentially, what I mean in almost like a SuperChems language is multiple dynamic PSVs. So that's SDF models or SDF boundaries. And what that is essentially a dynamic description of the movement of the spring. So if you have an upwards force on the spring, then the spring's going to lift up, allowing flow out through the PSV outlet. And then as either back pressure builds or you lose pressure at the inlet, the net forces act downwards, causing it to close. So we can build SDF models in SuperChems, and we can actually program that as a boundary in our new 1D gas models. And just to provide a little bit of context about the mathematics, as I say, I've got part of the detailed force balance and some of the equations that describe the motion of the disk in the SDF models down below. So how do we actually build the SDF models? Well, I've got a little graphic down at the bottom just to basically make it a bit more simplified. George has actually published a really great 5-part series on PSV stability analysis. And in part 1, he actually goes into great detail about how we can construct single degree of freedom models or SDF models. But I basically just wanted to summarize it for you all today. And basically what that is essentially it's you've got a complex force balance around the disk. And we have some data provided by, let's say, the manufacturers, and that could be the manufacturer of back pressure curves and some other geometrical parts and factors of the relief device, such as the spring lift, the valve nozzle area, discharge coefficients, valve weight. And what we can do is we can enter all of that data into the SuperChems PSV object, along with the back pressure curve. And using the detailed force balance, we can start to regress that information to get a dynamic lift profile of the PSV. So that's all built into SuperChems, and we can actually describe using these dynamics sort of descriptions and net force balances on the disk. We can describe how the disk moves dynamically with each of those forces acting downwards or upwards. So that's just a bit about kind of like, how we can create those sort of boundary conditions. And if we go back to our examples, as Charlie said, we've got 6 really interesting examples for you all. So Charlie went over the first 3, so more of the deflagration and hotspot creation side of things. As I said in the beginning of the presentation, I wanted to focus a lot more on the fluid mechanical side of things. So the first, I think, interesting example I want to cover is when we have 1D dynamics. The first thing I said is, we want to look into the more fluid mechanics side of things. Well, for me, a simple example of how you can use 1D dynamics is just in the case of fluid hammer and essentially sudden spikes in pressure and just essentially looking at those pressure waves. This example was actually published in that part one of the 5-part series that George wrote about PSV stability. He's got this example in here, and it's pretty neat. So essentially, we can create a 1D dynamic geometry of just a pipe, let's say. And let's say I've got a like an emergency shut-off valve or any valve really, and let's say I want to slam that shut. And I can actually see when the valve is being shut off. I can see the pressure wave essentially spike up, and then also how it can move back and forth along the pipe. And we can see at different almost like closing rates. So n equals 0.5 for closing time of 1 second. On the left hand side, we can see on the black line that the pressure wave is actually quite steady. That it's not actually that it's not spiking as much. But at faster closing rates, at a bit of more of a longer period of time, so basically the closing is going to get like speeds up as time goes on. We can see on the purple line at n equals 2, so that's quite a fast sort of crescendo of I don't know if that's the right term, but of closing rate. The pressure spikes almost quite quick. And that's a really important consideration in terms of, let's say, your piping design supports, and then also especially reaction forces. And we can see here on the graph on the right hand side, we can see that the pressure waves are all kind of reflecting off each other. And you can see it's a bit I guess coalesced at the moment. But the point here is that depending on your pipe lengths, you can actually get a lot of build up and interaction with the pressure waves going back and forth between the closed valve and the pressure source until it will eventually equilibralize and calm down. You can see it will eventually be very, very amplified, and then it will calm down as time goes on. Another few just cool examples. Again, these examples are very, very quite detailed, but I'll do my best to summarize them. Let's say you've also got, let's say, a shock in, let's say, a heat exchanger in this example. So, the shelf side pressure increases with time, and it increases quite rapidly. Let's say the tube side is like a gas, and we've got a liquid. The liquid's obviously going to get pushed out, so we're going to have some displacement. One key bit of interest is that sudden almost like pulse, or that displacement of liquid. How's that going to affect your process piping? Well, again, if we're being creative in how we use 1D dynamics, we can break up that process piping and use 1D dynamics to characterize the pressure pulse from the displaced liquid. And I've got an animation on the left-hand graph here, and then I've got the reaction forces on the right-hand side. But if we can just play a little bit here, we can see as time goes on, pressure's getting pushed right through. And I've slowed this simulation right down so we can better see it. But we can see as it's going through the process piping, the liquid's getting pushed right through, almost like as like a pulse, and then immediately it does calm down, and as that liquid almost like bulge gets forced through the piping. And we can see on the right hand side here, we do have a sudden spike in the reaction force. So again, it's a very nice example of how we can use those fluid mechanical principles and again in a creative way. So instead of just doing just a pipe flow analysis, we can actually think a bit more creative to simulate an event that I think most people wouldn't, I think imagine to use the 1D dynamics for. And then equally, we have a rupture disk case. Obviously, if you have a shock in a liquid full system from a tube rupture, then basically the liquid again is going to get displaced, and that could pop open your rupture disk. So again, we could just do the same sort of thing. If we take the rupture disk, we get a sudden spike in pressure at the entrance. That'll be the blue line. And then we can see a little dip on the red line. So to your right, you should see there's a red line, and essentially at the inlet of the rupture disc, you get a build up in pressure as you get a fast, almost like push of liquid to the rupture disc, and then essentially it suddenly pops open, and then the pressure starts to equalize as flows comes out of the rupture disc. So I guess that's a bit more of like an abstract use of 1D dynamics, but I wanted to, I guess, focus a bit more on the more traditional uses of 1D dynamics, and that is relief device stability, especially in single devices, and the main improvement in version 11.6, multiple devices. So if we just look at single devices and why we're interested in relief device stability, the main reason we're interested in stability is obviously damage to the valve, reduced flow, and I've got here, chatter in liquid systems, high pressure gas systems. You could cause severe damage to valves. You could cause severe damage to bellows. And you can actually reduce your capacity by as much as 50%. So that will cause a greater accumulation of pressure within your protected vessel during an overpressure scenario. So all in all, instability of your relief device is incredibly important. And in some cases, we do have simple tools, essentially as outlined in API. Now, this is an old, I guess, edition of API, but again, I think this overall, I guess, idea is still relatively true. You have the 3% rule, and then if you fail this 3% rule, you have other engineering analysis, including things like force balance checks, acoustic line length interaction checks, and then further more sophisticated methods such as 1D dynamics. Now, if we go down the more engineering analysis route as presented in the API standards, we can see here we've got the different levels, I guess, of accuracy and then sophistication. So again, 3% rule, simplify force balance and acoustic line length analysis, but then the 1D dynamics or the flow dynamics is on the right end of the spectrum, where we get the greatest amount of accuracy, but it does come with a lot of sophistication. The computational time is quite significant. So that's where things like force balances are very easy to use to at least screen the system to see if it's worth moving on to dynamics. But nonetheless, dynamics still very, very useful to see whether a system that was classed as, let's say, cycling in the force balance is indeed actually like stable or may actually have some flutter. So 1D dynamics in terms of stability, essentially what we do is we take the S2F model and we couple that with a PVT model. So that's essentially a reduced model of equation of state. And then essentially we take the inlet piping and outlet piping, chop those pipes into nodes so we can solve all those partial differential equations at each point. And then we essentially couple all of that together. So we stitch all those three pieces together, the inlet pipe, S2F model, and then the outlet pipe together to create a defined, almost like relief piping or relief system. And then we can then get a dynamic output, such as like mass flows, pressure, and things like that. I've just got like a nice example here. So I've got just a simple PSV. It's in liquid service. So basically we have a liquid relief case. And at the moment, it's quite close to the pressure source, as we see on the left-hand side. So it's about 1 meter. If I press the animation here on the right-hand side, we can see the relief device opens, but basically immediately it's pretty stable. Nothing's happening. You can see the PSV is opening because we've got a dip in the pressure here. But all in all, very, very stable. No fuss. It's all fine. But as we increase in length, we can see a very different behavior. So if I press the animation here, Okay, we're getting going with the pressure, the PSV is opening and closing, and we can see a coupling between the pressure wave motion and the PSV motion, so the movement of the disc going up and down. And when those two factors become intertwined, when they become coupled, essentially they become greater in sync. And then as they become greater in sync, they basically start to chatter. So what we're seeing now is almost like a chattering of the valve, and that's not what we want at all. And we can see the pressure spiking, and then we've got a bit of under pressure. And as I say, that is complete coupling, and that's just in terms of instability, that's it. We want to obviously make our systems more stable. If we go further in terms of length, it's a bit of a different story. So if I play the animation, we can see that as the PSV is opening, it's generating pressure waves. At the moment, it's probably going to be fluttering, right? Because it's generating those pressure waves, and it's fluttering with the disc motion. We can see the tip of the PSV here. So if I get my mouse, so right here's the PSV right at the end of the animation. But as time progresses, the valve motion, the relief device motion, becomes pretty much out of sync with the pressure waves, and that fluttering, that instability, then basically becomes almost like a quasi sort of stable behavior. So again, I'm just going to go back to certain parts of the animation. I'm going to just slowly scroll. Yeah, so we can see clearly defined pressure wave and PSV almost like coupling. And then as time goes, the pressure waves and the motion become way more out of sync. And then pretty much to almost like a quasi-stable behavior. And just to summarize the example, I also have this figure here, also again in George's white paper in the part one about stability. I think it's a really nice graphic here because it basically just shows how those different lengths can impact your lift and your lift profile and your stability. And we can see over there on the towards the 0.1 1.2 meter, sorry, 0.1 1 and 2 meter end of the diagram, it's pretty much stable. But as you get into that sort of middle territory, the basically neon blue and then pink line, so that's the 7 meter and 10 meter region, we can clearly see we've got that clear chattering in the valve. And then as we go further and further out, 15 meters, okay, we get some fluttering motion, but it's pretty much quasi-stable. And then 25, 50 meters, basically generate some pressure waves, but at that time it takes a long time for the pressure waves to come back all the way to the PSV. So essentially they are for all intents and purposes stable, but may not reach full lift and therefore full capacity. So that's how we can use it for single devices. But again, I think the really cool part is multiple devices. So how can we use the 1D dynamics for multiple devices? Well, again, just showed you for the one device. But again, if you've got like multiple devices, so again, in this example, I've got 4 devices. They're quite large in terms of size. We've got a piece, one at P set of like 4 bar, and then the others just slightly higher. We've got a closed boundary, so essentially the pipe is stopped after the 4th PSV. And then I've got a reasonable length of pipe, around about 20 meters or so, diameter around about 16 inch, just to provide a bit more of a greater flow area, just to make sure, the intent being to basically just keep all of the PSVs in motion. But as we'll soon find out that the system does indeed actually have problems when we use the 1D gas dynamics. So if I take this example, and then Charlie actually showed this briefly in his examples, what we can do is we can just define the system in a 1D geometry format. And we can see here, there's a C, which is the closed boundary. And we have DPRV spaced all the way towards the closed boundary. And that basically just stands for dynamic PRV. So that's where our SDOFs are all allocated. So if we take this geometry And oh yeah, no, here's just another screenshot to basically just show how we can allocate them. So there's like a little pop-up window in SuperChems, and we can just basically select which PRV we want. So let's take a look at the first result, I guess. So if I just let this run, that geometry run, this one, if I let this one run, we get a very interesting lift profile. Well, in that, basically, there's not enough, I guess, pressure to keep all of these four open. So, as they open, they relieve the mass, but essentially we have this huge pressure drop, and basically all of them start to basically chatter, and they chatter quite frequently. What's interesting, we can also see this in the animation. So if I play this animation, I can see that they open quite quick, but we can see they go up and down, and the pressure waves and the opening of the PSVs are all quite in sync. Now, what's interesting, I actually quite like this, is if I pause the animation here, and if I freeze it, oh, here, perfect. So if I freeze it, you can see the little bumps, and this is essentially when all of the PSVs start flowing material out. And it's quite a nice thing to see, because, when I think of, if I've got, four PSVs in a row and I want to look at mass flow and pressure, if I imagine a profile, this is actually kind of my sort of idyllic profile. So you can see PSV1 opens, PSV2, PSV3, PSV4, so they all follow the bumps. So again, very, very nice. But unfortunately, we do have the chattering in all four of the valves, and we have that coupling motion. So in terms of stability, it's not that great. As I mentioned previously, I chose 16-inch just for this example. So I wanted to say, well, okay, well, let's say I've got like quite a large nozzle. It's a big system, and I do have the opportunity to increase that piping, because let's say I'm reducing from, I don't know, let's say like a 20, like let's say 30-inch line, 32-inch line, and I reduced down to 16. Just hypotheticals. So I do have room to play around with the diameter there of the piping. So if I then increase the piping to, let's say, 24-inch, so go from 16 to 24, things do start to improve. We can see here on the blue PSV1, the lower set pressure one, it does chatter at the start, but then begins to flutter and continue as time continues. The red PSV2 right next to it, pretty much the same thing, chatters for a bit longer, and then it starts to find its footing and then calm down. And then basically the same trend basically just repeats itself all the way to PSV4, where basically we get some chatter, but then the chatter calms down and it becomes more of a flutter regime. We can also see a bit of that in hopefully in the pressure animation. So if I just run this a bit, okay, so we've got here, it's continuing, and you can already see the pressure isn't going up and down as quickly and as rapidly as previously. And we can even see it calming down quite a fair bit here. So again, just a bit more of a fluttering motion, not so much of a chattering motion, which is exactly what we want. And then just to, I guess, prove it a bit more, I went up just slightly higher, and basically the fluttering basically just disappears. We can see here the blue pops right open. The red has again a bit of chattering, same with the green valve and the orange valve, and then they pop open, but they basically calm down after that period of, let's say, 500 milliseconds, 1,000 milliseconds. But the key part of the new feature of the 1D dynamics is again basically manipulating the placement of the boundary conditions. So in this example, I took the 24-inch line. Now, if you remember, these PSVs were more bundled up to the closed boundary, that's C. All I've done is I've said, well, what if I don't want that? What if I want to put my first PSV close to the source, and maybe I split them all up all along the line? And again, you can test this all with the new 1D dynamics, and it provides, I guess, a greater dimension to system optimization. So if I continue, so with that new layout, again, we can see the blue blue valve, the low set pressure PSV1, basically pops open. We have that flutter. PSV2 chatters a little bit, gets a bit more flutter, but a greater, almost like a magnitude, it's a bit more amplified flutter. PSV3, PSV4 unfortunately still chatters. The reason for that was the closed boundary, having all those valves closer to the boundary, essentially for this 24-inch line, when the pressure wave gets to the closed boundary and reflects back, it keeps those other PSVs, those PSV3 and 4 closer to the end, keeps those open. So therefore, having them a bit more spaced out and a bit more away from the closed boundary causes that, I guess, imbalance of keeping the valves open on the further end. So then, I've went from keeping them quite close to the closed boundary, I've had them quite spaced out, and then just for completeness, I pushed them all over to the source. And again, we can see a very interesting result. PSV1 flutters quite a lot. PSV2 again flutters quite a lot. PSV3 does chatter, flutter, then goes back to chatter again. And then PSV4 just flat out chatters. And my reasoning for this is, as they're all bundled up, the pressure waves actually all become too coupled as they're too close together, causing this instability. It's almost like they're all kind of playing off of each other. So one PSV affects the other, and you've got strong coupling between these PSVs, causing the PSV3 and PSV4 to actually really chatter, which causes a huge problem. So again, the 1D gas dynamics, the new features in 11.6 allow us that greater malleability to optimize our systems for stability and to improve stability. Just a couple of conclusions, basically just summarizing what Charlie and I have explored with you all today. And then, of course, in the presentation, we just have some links to some white papers. But no, thank you all for listening, and I hope you have a great rest of your day.